Welcome, curious minds, to the deep dive. Today, we're really getting into how we power our world. It's crucial.
Hmm.
We're focusing on the big push for green energy, and specifically taking a closer look at two, well, powerful and often misunderstood players,
Mm,
nuclear fission,
the current stuff.
right, and the really futuristic promise of nuclear fusion.
Yeah,
We've looked at a lot for this, energy reports, scientific papers, even the studies on what people think, trying to give you the full picture.
absolutely. Our mission here is really to cut through some of the noise,
Mm-hmm.
clarify the science, which can get complex,
Definitely.
highlight some genuinely surprising developments, and help you understand what it all means for you, for the future, for the planet.
Okay, so let's set the scene. Our world, well, it still runs overwhelmingly on fossil
Well,
fuel.
it really does, despite everything.
Think back to 2017, oil, coal, natural gas. That was what, over 80% of our energy?
That's right. And the kicker, global energy demand just keeps going up.
Right.
Now, here's where it gets interesting. The global response. We're seeing this explosion of net zero greenhouse gas pledges from governments.
Covering a lot of ground, right? Like
Well,
70% of global GDP in emissions?
yeah, on paper, it sounds amazing, but, you dig a little deeper, fewer than a quarter are actually locked into law.
Ah,
And many, while they lack the specific policies to actually make it happen, it's more aspirational at this stage for many.
and you can feel the urgency, can't you? Something like 70% of people globally are worried about climate change.
Hmm. That pressure is real.
And it's driving this push for action, especially in electricity. Experts are saying that's where we need the fastest, biggest cuts.
Exactly. We're talking a 60% drop by 2030. Net zero generation globally by 2040. That is a huge, huge shift.
Monumental. So how are we doing on that? Renewables are part of the answer, obviously.
Oh, absolutely. They're growing incredibly fast.
Yeah.
2024 saw a record 18% jump in global capacity, 741 gigawatts added.
Wow. Mostly solar.
Yep. Solar PV took the lion's share, 81% of that. Wind added a big chunk too, 117 gigawatts.
Mm-hmm.
And China, they deployed 60% of all that new capacity.
60%. That's massive.
It is. But even with that incredible growth, the projections show we're still likely to fall short. About 800 gigawatts short of that international goal to triple renewables by 2030.
So why the gap? What are the roadblocks?
Well, challenges like grid saturation, just getting all that power onto the grid smoothly,
Yeah.
and financing these huge projects, that's always complex.
This brings up something really important, the capacity factor. It helps explain the differences, right?
Absolutely critical concept.
Yeah.
Nuclear power plants, they run almost constantly,
Yeah.
near 100% capacity factor, just churning out power.
Whereas solar, well, the sun doesn't always shine, right? Weather impacts it,
Yep.
lower capacity factor.
Exactly. But there's another player that's interesting here, geothermal energy.
Right, tapping the Earth's heat.
Yeah, it's clean, it's dispatchable, you can turn it on and off when needed, and it has high capacity factors, maybe 70, 80%.
And potentially big growth. I saw figures like 800 gigawatts by 2050.
In some scenarios, yes. What's really intriguing is the link to the oil and gas industry. Their expertise in drilling, completions, that could really help bring costs down for geothermal.
That makes sense. Transferable skills.
Definitely. And it's not just about generating power. For a full net zero picture, especially for those hard-to-electrify sectors, we need other tools.
Like carbon capture, CCUS.
Exactly. Carbon capture, utilization, and storage. And developing low-carbon hydrogen. These aren't just buzzwords. They're pretty essential parts of the puzzle.
Okay, let's unpack the nuclear family then, because people hear nuclear and might think it's all one thing.
Right. But it's really two fundamentally different processes. First, there's fission.
That's the one we use now, in power plants.
Yes. Fission is about splitting a heavy atom's nucleus, like uranium. That split releases a huge amount of heat.
Like breaking a stick, releasing the energy stored inside.
Good analogy.
Hmm.
That heat is then used to make steam, drive turbines, generate electricity. Standard stuff, technologically speaking, in terms of power conversion.
Okay. And the other one, fusion.
Fusion is the opposite. Instead of splitting heavy atoms, you're combining light ones like isotopes of hydrogen.
Like squishing them together.
Exactly, under immense pressure and temperature. That's what powers the sun and the stars. It releases even more energy than fission.
The ultimate clean energy dream, people call it. Limitless fuel, no long-lived waste.
That's the promise. But, and it's a big but, it's still experimental. We haven't cracked how to do it commercially yet. The challenges are immense.
Yeah, there's that old joke, right? Fusion is 30 years away.
And always will be. Yeah, we've all heard it.
But things are changing. I heard about a big breakthrough recently in net energy gain.
Ah, yes. At the Lawrence Livermore National Lab, LLNL. A huge step using inertial confinement fusion.
What does net energy gain actually mean in this context?
It means, for the first time in a controlled experiment, they got more energy out of the fusion reaction than the laser energy they put in to start it.
Wow. So proof of concept, finally.
Exactly. Many are calling it the beginning of a new era. It proves the fundamental physics works on that scale.
Okay, so how are scientists actually trying to make fusion happen? You mentioned inertial confinement. Are there other ways?
Right. There are two main paths researchers are taking. The first is magnetic confinement. This mostly uses devices called tokamaks.
Tokamaks. Sounds like something from sci-fi.
Yeah. They were actually designed by Soviet physicists back in 1951, still seen as the most promising design generally. They use powerful magnetic fields to hold superheated plasma, think ionized gas in a donut shape.
Plasma. How hot are we talking?
Millions of degrees Celsius. 10 million.
Wow.
Sometimes much higher. Hotter than the sun's core.
Okay, holding that seems difficult.
Extremely. And managing instabilities in the plasma is a huge headache. One major issue is something called an ELM edge localized mode. Yeah, imagine the outer layer of this super hot plasma suddenly burps out these intense bursts of heat and particles.
Uh-oh.
Yeah, uh-oh is right. These bursts can hit the reactor wall with immense power, like 10 times more than the materials can handle. So controlling those ELMs is absolutely critical.
So that's magnetic confinement, holding the tiny sun in a magnetic bottle. What's the other way? Inertial confinement, the LLNL one.
Right. Inertial confinement fusion, or ICF. The idea here is different. Instead of holding plasma steady, you take a tiny fuel pellet and blast it symmetrically with incredibly powerful lasers.
Compressing it.
Exactly. Compressing and heating it so fast that fusion happens before the pellet blows itself apart. It relies on inertia, hence the name.
And within that, there's this fast ignition idea.
Yeah, that's a refinement. It tries to separate the compression stage from the ignition stage. Compress the fuel first, then hit it with another ultra-intense laser pulse to spark the fusion. It could potentially lower the total energy needed to get it going.
Sounds incredibly complex, but that LLNL result shows it's not impossible.
Precisely. And that success, along with others, is fueling a lot of investment. Global fusion funding hit over $7 billion in 2024.
Mostly private money now, I read.
Increasingly, yes. Private companies are jumping in big time. You've got companies like General Fusion aiming for break-even, getting as much energy out as they put in overall by 2026, and a commercial plant maybe early to mid-2030s.
Ambitious timeline.
Very. And others, like Proxima Fusion, are working on advanced stellarators. Another magnetic confinement design also targeting the 2030s. The private sector race is really heating up.
What about the big international projects? ITER in France, that's supposed to be the flagship, right?
It is. ITER is this massive international collaboration designed to demonstrate sustained fusion with significant energy gain. But it's faced major delays and cost overruns.
Yeah, I heard. How delayed is it now?
Operations are now expected around 2027. That's about 11 years later than originally planned. It just shows the sheer scale and difficulty of the engineering involved, even with global cooperation.
Right. It's a monumental challenge. Okay, let's switch gears back to fission then. The established workhorse.
The one that actually powers homes today.
Exactly. It has a long history, right? Since the 1950s. Grew pretty quickly for a while.
It did. By 1990, we had about 300 gigawatts installed globally. And even in 2023, it provided 9% of the world's electricity.
Still the second biggest low-carbon source after hydro.
That's right. A significant player.
But it comes with history. Accidents, 3 Mile Island, Chernobyl. Those cast a long shadow.
Absolutely. Those events led to much stricter regulation and, understandably, a rise in public opposition in many places. Fukushima also impacted public support, especially in Europe.
Yet you're seeing countries reinvesting now, France building new reactors, the U.S. too.
Yes, there's definitely a strategic reevaluation happening. Many countries see it as a reliable, low-carbon power source that's essential for meeting climate goals and ensuring energy security. France is planning 6 new ones by 2050. The U.S. has advanced reactors planned for 2027. It's a comeback of sorts.
And the modern plants, they're pretty impressive performers, aren't they? I saw some stats. 60-year lifetime.
Yeah, the designs like the NPP 2006 standard aim for a 60-year life. Incredibly high load factors like 92%, meaning they're running almost all the time.
99% availability, less than one unplanned shutdown a year. That's reliable.
Extremely reliable. That's a huge plus for grid stability compared to intermittent sources. You have designs like the Advanced Boiling Water Reactor, the ABWR, that's a generation of the rest design, already operating commercially in Japan, licensed elsewhere too.
And we're already looking beyond Gen the third, right? Generation the fourth
We
reactors.
are. Gen the fourth is the next frontier for fission. These are mostly in the design phase, aiming for industrial deployment around 2050. The focus is on major improvements, sustainability, safety, economics, and crucially, proliferation resistance.
What kind of designs are we talking about?
Well, one exciting area is molten salt reactors, MSRs.
Molten salt instead of water.
Exactly. They use molten fluoride or chloride salts as the coolant, sometimes even with the fuel dissolved right in the salt. This offers potential safety benefits, and significantly, they might be able to burn some of the long-lived radioactive waste, the actinides, from current reactors.
Burn waste, so less problematic leftovers.
Potentially, yes. Extending fuel resources and producing waste that's radioactive for a much shorter time. Then you have concepts like supercritical water-cooled reactors, SCWRs, using water at very high pressure and temperature for better thermal efficiency.
And what about different fuels? I keep hearing about thorium. Is that a real possibility?
Thorium is definitely getting a lot of attention. It's much more abundant than uranium in the Earth's crust.
Okay, that's a plus.
And it's what we call fertile. It can absorb a neutron and transform it to a fissile isotope of uranium, U-233. This conversion is actually more efficient than breeding plutonium from uranium in current reactors.
So potentially much more fuel available.
In theory, yes. If we master thorium breeder reactors, we could stretch nuclear fuel resources by maybe over 100 times. India is very interested in this because they have large thorium reserves. They're actively working to commercialize it.
Okay, if it's abundant and efficient, why aren't we using it everywhere? And this brings us back to the waste issue. That's always the big concern people raise with fission.
Good points. On thorium, well, developing and commercializing the whole fuel cycle, especially the breeding part, still requires significant R&D. It's not quite off-the-shelf technology yet.
Right, and the waste.
Okay, waste, it gets categorized. Low level is stuff like contaminated clothing, tools, manageable. High level waste is mostly the spent fuel rods. Highly radioactive stays that way for thousands of years. That's the main challenge.
So perspective is needed, though, right?
Yeah.
How much of this waste is there compared to other industrial waste?
It's important context. In countries with nuclear power, radioactive waste is actually less than 1% of their total industrial toxic waste. And interestingly, coal plants can release more radioactivity into the environment through fly ash than nuclear plants do during normal operation.
That is surprising. So how do we manage the high-level stuff now, and what's the long-term plan?
Right now, it's mostly interim storage. Spent fuel sits in cooling pools at the reactor site initially, then often moved to dry cask storage, also usually on site. Very secure, but not a permanent solution.
So what is the permanent solution? Underground repositories.
That's the internationally agreed approach. Deep geological repositories, burying it hundreds of meters down in stable rock formations. Research is also looking at deep boreholes, even deeper disposal. And those advanced Gen the fifth reactors we mentioned, some could potentially use existing spent fuel as their fuel.
But we don't have any of these deep repositories operating commercially yet.
Not for high-level waste, no. Finland's Onkalo facility is the furthest along. It's under construction. But finding sites that are geologically suitable and have public acceptance has been a massive hurdle globally.
Okay. And the other hurdle, cost. Building these plants is expensive.
Very. We're talking US $6 to $9 billion for a large 1,100 megawatt plant. Huge upfront capital cost. Although costs did come down in places like India and South Korea for a while.
So government support is key. Low-cost financing.
Absolutely essential. Just like renewables benefited hugely from government support schemes and access to cheaper financing to get established, nuclear needs that level playing field, especially if it's going to contribute significantly to the low-carbon transition.
This is where the smaller reactors come in, right? Small modular reactors, SMRs.
Exactly. SMRs are a really key development here. These are much smaller, maybe 50 to 500 megawatts, designed to be largely built in factories and then assembled on site.
Factory-built nukes.
Kinda, yeah. The idea is mass production brings down costs, shortens construction times, makes financing easier. They're more flexible, too.
Flexible how?
Well, they could be used on smaller grids, replace old coal plants, provide power behind the meter for large industrial sites, generate high-temperature heat for industrial processes like hydrogen production, even potentially power remote communities.
Well, it's not just big central power stations anymore.
Right. It opens up new possibilities.
Yeah.
Now, SMRs are moving from concept to reality. Licenses are being issued, some are under construction, but their major impact on climate change, that's probably more towards the late 2030s and beyond.
Are there actual projects underway? Examples?
Oh, yes. India has its Farad Small Reactor Initiative, looking at 220 milli reactors for industry, hoping for climate finance support.
Okay.
In the U.S., the Department of Energy is funding demonstration projects from companies like TerraPower and X-Energy, aiming to have them operating by 2027.
Hmm.
And GE Hitachi's BWRX 300 design is being deployed in Canada right now. So, real momentum.
That's fascinating. But what about public opinion on these? Are people more accepting of smaller reactors, maybe closer to where they live?
It's a mixed picture. A survey in the Czech Republic was interesting. It showed pretty high general support for nuclear year. 65% had few concerns. 70% thought its use should increase.
That sounds positive.
It is, overall. But when asked specifically about SMRs near their homes, older people and women showed less acceptance. So that proximity issue, that not in my backyard feeling, it's still a factor, even for smaller designs. Community engagement is key.
Right. Now, this whole energy landscape, especially nuclear, it doesn't exist in a vacuum. It ties into geopolitics, doesn't it?
Oh, absolutely. Energy security is national security. And choices about energy technology, particularly nuclear, which has dual-use potential, are deeply linked to global competition.
We're seeing this with China, for instance. Sources mention a significant nuclear weapons buildup.
Yes, the projections cited suggest China could reach around 1,500 nuclear warheads by 2035. They're also advancing naval capabilities like new nuclear attack submarines and hypersonic weapons.
And this creates challenges for arms control, with existing treaties like New START expiring.
Big challenges. The U.S. and Russia need to figure out the future of their agreements, and the U.S. has been trying to engage China in talks about strategic stability, managing nuclear risks, preventing accidents, even covering things like cyber and space attacks.
It's important we just report these facts impartially, right? Not taking sides.
Absolutely. These are the strategic realities outlined in the source materials. This competition isn't just military either. It's heavily playing out in energy investment, too. China is pouring money into renewables and nuclear as core parts of its future strategy.
Wow. Okay, what a deep dive this has been. We've covered so much ground.
We really have.
The huge challenge of the global energy transition, the incredible promise, but also the ongoing hurdles for fusion.
Still maybe decades away commercially.
Right, and then the evolving role of fission, its history, its challenges, but also its potential resurgence, especially with these new SMRs.
And connecting it all to the bigger picture,
Oh.
it's vital to remember something. While we're investing a lot in today's clean energy tech, a big chunk of the emissions cuts we need by 2050, they depend on technologies that are still being developed, still in the lab or in pilot stages.
So innovation is absolutely critical. We can't just rely on what we have now.
Exactly. Continued R&D investment across the board, it's non-negotiable, really.
Indeed. Which leaves us, and you, the listener, with a final, maybe provocative thought to mull over. Given all these complexities we've discussed, the immense potential, the serious challenges, the costs, the timelines for both fusion and advanced fission, how do you think humanity should prioritize its energy investments moving forward? Where should we place our bets to get to that sustainable, secure, and prosperous future we all want?